recoverably about 0.8% strain, so you bend your spring, if you like, within 8% strain, let it go and it'll spring back. This material, however, approximately 10 times more. You can go to 8, arguably more percent, which means effectively I could have a wire of the superelastic binary alloy, for example, tighten a knot, tighten it, so it really is tight, let it go, and it will spring open again if I let it go without a kink in it. You couldn't do that with the other comparative elastic materials. Now, both properties are of value in the commercial arena. You may have seen they're very widely used now, these spectacles which you can bend, you can sit on them if you like, and they recover elastically. It's big business out there, and I'll come to a lot of other various applications, many of which use these superelastic properties. So the thermally induced material, superelastic material, these two generic types, the essential way of putting the memory in is to constrain it in the memorized shape you require and cook at 450 up to 600 degrees C, and that installs the memory. You cool it down and then the memory is there. You can go for an awful lot of different cycles, depending, operational cycles, functional cycles, depending on how much induced strain you put into the material. I'm dealing with things which have to, through small strains, have to withstand well in excess of 400 million operating cycles. These are medical implants, which I'll come to in a moment. Okay, so just to repeat that, the function of the material is you've got the original straight, a piece of wire, for example. You set the shape, 450 degrees C, using a jig of some kind. You mechanically deform, and when you warm it up again, it remembers or it recalls that original shape. It's fairly straightforward. The metallurgy is actually quite complex. The uses in the space program on various vehicles are manifold. This is an example. I've given a short list, and indeed the latter one, it was referred to a moment ago, Rosetta, launched almost a couple of years ago now. It's been launched, it's done a slingshot around Mars, taken some absolutely wonderful pictures. It's been back to Earth, done a slingshot, and it's now flying out to its final mission, which is a Comet Rendezvous mission. Now, on board that, and in conjunction with my colleagues at RAL at Rutherford, they approached me because they had a problem. On board Rosetta is 50 bar pressure ultra pure helium, which is used to recondition or recommission after 9+ years of being rather cold and lonely flying. Some of the scientific instruments that do material analysis when it rendezvous with a particular comet just the other side of Jupiter. And we created something, the shape memory alloy leak-proof valve, because helium, of course, atomically very small, and it does leak. This has all been hardened up. It's flight harder, and it is actually flying now. I know the system has been tried successfully, and I guess because I was the sort of concept driver for this particular artifact, by the time it rendezvous with the comet, I don't know, perhaps I won't be on this Earth, but that may be a good thing, because if it doesn't function, I'm in real trouble. But it will. I'm very confident. Some of the other things from way back here, typically things like antenna or solar array deployment. Simple actuator. When I say simple actuator, I mean the heart of it is a simple actuator, but implementing that is a little bit more complex. Aerospace shutoff bidirectional valve, 5 grams total mass, electrically operated, a little diaphragm, which is heated. It deforms and exposes an orifice, a hole, if you like, where a gas can pass through. Semi-rotary actuator. If you can think of this material, incidentally, it comes in many, many different forms, and the way you put memory, or the geometry of the memory, is only limited by imagination in many respects. You can have tensile, compressive, torsional forces. It's fairly straightforward to do that. Pipe coupling, it's most of you that have taking an aircraft trip, let's say Boeing 737-200 series, and I think maybe 400 series, be aware when you're at 39,000 or 37,000 feet, you are relying on shape memory alloy fuel line pipeline couplings made of shape memory alloy. The small animation there, if you can imagine that piece of pipe is actually in two pieces and you need to join it together. So a shape memory alloy ring is put on cryogenic or cryo temperatures. It's brought up to the aircraft in a bucket of liquid nitrogen in a deformed state. It has a memory of being a little bit smaller, clamps down, producing sufficient hoop forces on the pipe to seal it. This has also been used in the cryogenic or the cryo area on a number of spacecraft to seal two pipes which need to be connected essentially. Okay. Other forms of sealing devices and clamping devices for sealing electrical cables in if I can call them high-value applications or critical applications like a spacecraft or a space vehicle of some kind. There's plenty of these, many commercial companies now making these sort of things. Something I was involved in, completely moving away from the aerospace, how to split rocks open in the high-value, I choose my words carefully, high-value ores in the quarrying industry. We use shape memory alloy actuators because they're very energetic. The schematic I've shown here, a solid cylinder, half an inch in diameter, 12.5 millimeters, 12.7 millimeters diameter, is compressed in a hydraulic press, about 8 metric tons to compress it, heat it up to 80 degrees C, and it gives you back 6 tons over a length of 1 millimeter approximately. Small strain value, relatively small strain value induced in the material, so lots of cycles, and you put a whole series of these, equally as shown at the top, into a steel holder. It goes in a pre-drilled hole inside a metrology granite, for example, to give very accurate rock splitting. This is an EU-funded craft project with a whole series of companies across Europe, but all using nickel titanium shape memory alloy. There's my superelastic spectacle frames, anti-scald device. Clearly this material has applications as an essential thermostat because application of heat, it expands or contracts or does whatever you want to do. Your domestic kettle, in this case a Rowenta, several of these are being used. SMA, shape memory alloy, orthodontic arch wires for teeth correction measures, a strange sort of fishing line which is selling quite a lot by a Japanese company, Furukawa in Japan. Apparently if you go fly fishing, and I'm not a fisherman, you send your fly out and the fish takes a bite, and instead of having to play the fish by reeling in and just making the poor fish worn out, it uses the elastic, very extended elastic properties of this line. It swims away and you just stand there waiting for it. It then has the time for recovery. It then swims away and eventually it's completely worn out, then you just reel the whole thing in. You may know about this this top application, the underwiring in braziers. Again, it's actually quite big business. Not something I'm involved in, I have to say, but quite big business. These elastic things give better support. Another thing to say, because of this, incidentally, is the superelastic material is non-Hookean in its performance. It's effectively a constant force spring. It's